So let us start our discussion with the paper one. So what I've done here is I've scribbled some handwritten ideas for all of you for the complete paper. So as you tell me the question number, I'll start discussion on that. So any question in paper one of GTA 10 in physics?
Fourth one.
Fourth question. All right. Let us look into the fourth question. Now, if you look into the idea of the question, the idea was straightforward. Like what he wants me to analyze is, if this is the cylindrical patch which is given to you, he wanted me to find out the limiting ray, right? Where the ray which is having a TIR is going to fall. So we understand that if for a location, the ray is tangential to the surface and it falls here, then with respect to points which are above and below, like if you go to points which are above here, the angle with respect to normal is going to increase, right? So they are going to execute TIR inside. So they are not going to go outside. And if you go below, they're going to come inside. So basically, he was just talking about the length of the illuminated patch. So what I have scribbled here is a simple thing. I tried to calculate the theta c for the system, and given the values, theta c came out to be 60 degrees. If you look into the values, it was 2 by root 3. So sine inverse of root 3 by 2, that was 60. And when I got theta c as 60, and this was my tangential ray, which is hitting here, then I did some basic calculations. I got this angle as 60. I got this line. I got this angle as 30, right? Again, this angle was known to me. That is 90 here. So this angle was 60 for me. This value is R. So now things were simple. This was R root 3 by 2. And this is R cos 60. This angle is also 60. So this value was R by 2. This height as such was R root 3 by 2. And then because this is 60, this total length came out to be 3R by 2. Now obviously this location was R. So this distance was again R by 2. So basically what was the length of this value? So it will come out as R. R will be your answer. Next.
In question number 3, angular momentum conservation is valid, sir.
In question number 3, actually in 3, the problem that is happening is he has presumed that there is a force which is of a given nature, which is of the similar nature as that of a gravitational or the electrostatic force. So his question was something hypothetical. What he was trying to tell is, if there is a fixed ring and there is a point of fixation about which hypothetically a particle is moving. Now let us be very clear about this problem, that there is a supposition, this is an assumption. This is not a natural force which is acting in such a way. So he's presuming that if there is a force which is directed towards a given point and he has taken a circular path which is not even elliptical, because in real life, when such forces are going to act, the body is going to follow a unique path. So you can assume that there is a machine which is being kept here, which is consistently applying forces in such a way that the variation is known to you. So this machine is, by means of some power which you are supplying from outside, it is generating this artificial force which is of this nature. So that is why the only idea that I have used here is work energy theorem. I mean, all the forces which are acting on this body, I've just written the work energy theorem and I've ensured that the forces which are acting towards it, if I can ensure that this guy starting from this point just reaches this point and crosses it, my purpose is solved. So after comparison with the electrostatic potential energy or the gravitational potential energy, because the nature is attractive, that's why I've written a potential energy to be negative, and I've conserved the energy between these 2 points and got my result. Any thought process which is beyond that is not directly applicable. The reason being, the real life nature of this force and the path is not given to you. So he has generated, because you don't know, is it a charge? You don't know, is it a mass particle? You don't know the nature of this guy. Why he is generating such a force where the particle is moving on a circular path? So because the motion was given to be circular. So I just applied the basic funda. That is, I can apply the Newton's laws on that particle or the work energy theorem. I got my answer from work energy theorem. I think you understood this idea, na? How I've written these equations?
Yes, sir.
Yeah, potential here, potential there, and just balance the energy. That is the work energy there. Just think of anything that is coming to your mind. I mean, these are my scribbled solutions. So if I would have been solving the paper, these would have been the solutions I would have been writing. So you can also take a glimpse of like any other question in paper one, or should we like
12th one.
12th question? Okay. 12th question was nice. Here the data is such that, yeah, it's like these are 2-point sources from where sound signals are coming, and you're talking about generating a minima on this line. So what I've done here is, if you observe carefully, that I have gone to a general point X and I've taken a wave straight coming from here and the other coming from here. So if this distance is d, this is x, I've written the part difference here. So I wrote it as root of d square plus x square, you can see, minus x is equal to odd multiples of lambda by 2. So instead of, I generally wrote it like odd lambda by 2, the first location, the second location, third, so on. So as I'm moving from infinity, you understand that the part difference is increasing, because at infinity the part difference tends to 0. So I'm trying to write these terms from infinity towards this point. So then I kept on solving this odd lambda by 2, and we understood that if you are coming from minus infinity up to this point, so we are searching for all the locations except the location where odd lambda by 2 is equal to d. So I use this inequality that odd lambda by 2 should be less than equal to d. Why I've written that odd as 2n minus 1? Because you understand the first location, I mean, n here represents the location number, the first minima, the second minima, and so on and so forth. So I kept on solving these equations, 2n minus 1. I got this inequality, n should be less than equal to d by lambda plus 0.5. So then I checked the answer. I got the n max value, that is d by lambda plus 0.5. A option was correct. And then just I wrote some possibilities, like where exactly will I have the minima. So I got that I took x on the right hand side and squared it up. D square plus x square was x plus these odd lambda by 2's, the squares. So I just wrote a general equation like these are the possibilities. X square is equal to this. And then I checked the possibilities. So if you see, you will obviously observe your answer, which results were coming. So these were the ideas, the 2 ideas to check. Last one, you understand why I've written this, because I was moving from minus infinity towards this place, and this was the final inequality I have to check. And n is the first location, second location, location number, to be honest. So n is the location number, my location number. Any other question?
10th question,
Paper
C
one.
option.
10th. Okay, I should go back and take up 10th. 10th was this. Let me tell you what exactly is happening directly. By the property of conductors, I'll solve this question. What happened? I'll directly say there's a Q1 which is kept here. Then there is a solid sphere. This guy is having a cavity. Inside the cavity, you have kept a charge Q2 at the center. So minus Q2 will be uniformly induced here. So we'll have some minus Q2 here. Let it be that way. Then to this solid, you have supplied a charge of Q3. So what is going to happen is, I mean, minus Q2. So you will have on the external surface, there will be some negative charge here. There will be some positive charge here. Howsoever non-uniformly distributed, but this negative, positive in totality, because here we have minus Q2, it should be plus Q2 and additional charge plus Q3. So inner surface and outer surface of this conductor in net should have a charge of Q3, because Q3 has been given. So because there is minus Q2 here, so I've taken plus Q2 plus Q3 in net. Now the question. The first question was, what is the potential of the sphere? So I'll try to write the potential at the center of the sphere. You just check what I've done. So I said at the center of the sphere, even if after non-uniform distribution, the total potential will be this thing, K Q2 plus Q3 upon 2R. And then I have written because of Q1 at the center. So this is this much. And what about these guys at the center? These guys will have a 0 contribution there. Why? Because by the property of conductors, the charges which are present inside the cavity of a conductor and on the inner surface cannot produce any field or potential outside their body, outside their domain. So that contribution was 0, simple. B option. Potential at inside the cavity at any distance smaller. If you go at a distance smaller here, remember one thing, the potential of the conductor that you have written previously will remain as such. So answer of A part will remain as such. And then I have to write additional term. So if I'm sitting at a distance of smaller from Q2 and I try to enter this cavity, I will do additional work there. And that additional work is this thing, the potential difference because of the Q2 charge. So K Q2 upon R minus K from where I'm moving, that is K into inner surface Q2 divided by R. My contention was, if you look into the expression there, B option, that was not matching because I directly saw that in A part you have Q3 term also, and B part he has not written that term at all. So I was not even interested in looking into the options. Understand, while you are moving from this point to an inner point, you are doing some additional work, which is basically the potential difference because of this setup. And I'm saying the potential difference there will be the final potential. The final potential is K Q2 upon R and minus K Q2 upon his radius, and his radius was R by 2. You understand why I've written this term here. This is additional work and A part, so it doesn't match. C part. Obviously, the value of potential outside the sphere at a distance R from the center of the sphere is, if I want to write potential outside somewhere, let's understand what I should do. I can write potential because of Q1, perfectly fine. He has written K Q1 upon R prime, I accept it. But then he has written potential K Q2 plus Q3 upon R, not acceptable. Because of this guy, it is 0, I accept. But the third term that he has written cannot be written that way. That is possible only if Q2 plus Q3 is uniformly distributed on the outer surface. Then someone can say, sir, fine. Is this a possibility that for a given R it is valid for one of the points? Maybe, but that cannot be a general statement. So we cannot accept it generally. That's why it is not right. What about D? How much charge will flow into the ground? So I just calculated from basics. How I calculated this charge was, initially, I knew what is the distribution of charge on the outer surface. I know the total charge initially. And the final state, what I did, I presumed how I got these values. In the final state, I presumed that it has been earthed. After earthing, I wrote the potential at the center to be 0. And that was K Q1 upon 3R plus whatever charge is present on the outer surface, I assumed it to be X. So Kx upon 2R, that is equal to 0. Because this guy cannot give me potential at the center. Somebody can say, why are you writing potential at the center? Because the body being earthed, I can write potential anywhere on this conducting sphere. So I chose the center because writing potential is the easiest because of non-uniformity of charges. So I got the value of X on the outer surface, which is minus 2 Q1 upon 3. So then I understood the total charge on the outer surface initially was Q2 plus Q3, and now it is minus 2 Q1 upon 3. So whatever is the change, final minus initial, that is from Earth. So Earth will supply this much charge. So if you look, D option was correct because Earth is supplying this much. So Earth is getting the reverse. So D option was. Next. This is fine. We can do paper 2 also.
14th.
Yeah, wait. Which problem? Wait.
14th.
14th. Okay. Let me take up question 13. 14. Yeah, this is nice problem. Because these voltmeters are ideal. Look at the method I have adopted. I have done zeroing of the circuit. I took 0, 0, 0 here. I take 9, 9, 9 here. I know they are ideal voltmeters. So basically the current through them is nearly 0. So I assume that to be 0 throughout. And then I wrote potential 9, 6, 3. 9, 6, 3. Then I said, this is under assumption. Then I said, no, some current will flow. So presume that to be X now. So after assuming that these potentials are like 6, 3, 3, X, then I have applied the Kirchhoff current law. I have written current here, current here, current here, and I've done the sum to be equal to 0. This is resistance of voltmeter. I got the value of X. X is 4. And if X is 4, what is the value of V3 was the question. So maybe X minus 6, like this guy is X minus 6 mod. So answer is 2. I mean, you have to intelligently think. I mean, first, you know that these are, they will have some current, but that is tending to 0. So initially I've assumed the current to be 0. So I've written all the potentials. And then I said, no, some current will flow. So let me assume that potential to be X. And then I have applied the Kirchhoff's current law. I got the value of X and the answer. This was a bit calculative. If you look at 17, I mean, there are other methods also. But the first idea that came to my mind as a student, if I would have been solving, I would have written this equation of dq is equal to du and just done a bit of calculus, and I got that coefficient very easily. Rest was pure calculation. I think we are done with this paper. So we can go to paper 2. Any question in paper 2? Anything comes to anyone's mind, you can stop me and I'll elaborate that solution. This was a nice one. If you look into the spring problem, I mean, bit of basic calculus like balancing situation, go a further distance x, look into the restoring force, take binomial approximation, get the force. Then you have to just write the delta U of spring and delta U electrostatic and substitute the initial conditions properly. And you get those mod that he has discussed to be equal. So out of D and C, C was correct. Right. Rest was like based on very simple formula, half of reduced mass into Ural square. That was a very standard problem. And any question you want me to discuss out of these 9? This was equivalent EMF, equivalent internal resistance. One line question. This was based on a very fundamental rotational problem. I just scribbled a bit and solved for that. I mean, where is the direction of friction? How to find out the direction on the basis of magnitude, what is going to happen? So ICR concepts I have used, and then V is equal to U plus AT. And finally, I just checked which direction friction is going to act. So the reason why I've scribbled this is also to tell you how you should go about solving a paper at the topmost level. I mean, this will give you a very fair idea of how a student should like do rough work also, like what point he has to note, how to strike off the given options. If you look into the order in which I solve, like I never like for multi, I don't always go for ABCD. I look into the ideas where I can struck off easily, and then I'll go to the remaining option. So very fair idea. It will give you the how much you have to think and which directions. Like it was based on conservation of momentum and energy equation, and this was a nice problem. The collision happens there, and then whole after the till the first collision they go straight, and then when they jump in that situation, he will just give his full energy to the upper guy under the situation given, and then I have just used coefficient of restitution to be equal to 1 and one equation by momentum conservation. I got my I got that relation which was required. This was nice problem based on gravitation, the 14th one. So here I have just taken the relative concepts. Relatively, the bead has to move x naught. It is half of ARL into T square. And to calculate ARL, I just did a bit like to calculate A rod, what I have done on the rod, at every differential element, I have calculated the gravitational force by integration and divided by the mass of the rod. So I got an acceleration term. And for the bead, I have written directly. And I say for those small distances, with respect to the distance from Earth, the variation is not much. So we can take constant accelerations in that small domain. Then it was quite simple that I got my x naught expression like this. After writing A rod and A bead carefully, A rod was more typical because for that I have to do a bit of integration. And I have not directly concentrated the mass of the rod at the center of mass because there is no such concept in electrostats or gravitation. Where to calculate the force, you concentrate the mass on the center of mass, you can't do that. So I've done the basic calculation. If you understand this first step, then it is purely maths that I've applied. I got these equations. Then I did some binomial approximation here. I took R naught out and I just kept on solving with approximation. Then it was purely calculation and you got your value of T. This was again a nice problem which was based on angular impulse. That if you just the torque that was being generated, so I've written that n mu b term dt in differential time, that was a change in angular momentum. So then I calculated the omega f, and I think it was quite obvious after that because this mu can be written as current into this idt term was the charge that has flown, and then the moment of inertia I've written here. And I think you will get this. This was 2 by 3 here. I substituted here 2 by 3. And I kept on solving here. After that, calculation of time. This is the gravitational problem. Then I went to this question number 15. That was based on the displacement method. You understand very easily. Two different positions. Magnification becomes reciprocal of each other. I just calculated it and simply shifted twice. Like you understand, I have taken it here, but I knew that this was negative because in the second case, I have taken more distance from the left-hand side. So that's why I took a mod. So because in the first step, I've written this was just to overcome that. Rest, it was a very simple equation. Two positions. And this was purely symmetry method and get the result. And 18th was like, I think, what was that question? 18th problem there. Yeah, that was simple. If there is a current which is flowing in the outer circuit, that will produce a magnetic field. So mu naught into current upon, I had taken resistance per unit length as lambda. So lambda into 2 pi capital R, that was current. So mu naught into current upon 2, that was magnetic field. Magnetic field, magnetic flux, rate of change I have calculated, and then just 1 upon resistance. So that was correct. Now you can, I have scribbled, shown you everything. So now any specific question you want, I'll discuss that. In paper 2, any specific question is coming to your mind, you can ask, I'll elaborate on that. And if it is fine, then we can. So because I've scribbled this at a very high pace, so maybe at times I have to just cut something. So maybe if you present it, your presentation may be simple, but I have not bothered about that. I'm just focused on solving objective paper, so not on the presentation of my solution. So, and at this stage, you should definitely look into these things because we are nearing towards JEE Advanced. Any concern in the paper, any question, then I'll carry on, or then otherwise I'll just. I think we are done with the paper. So okay, students, fine. Then I'll see you all again in my regular class. We'll keep on solving some nice problems there. Take care. And this was a nice paper. And I think as far as the top 10 rank is concerned in physics, if it was 66, 132, so maybe a score of out of 132, anything which is above 120, right? Greater than or equal to 120, maybe a single digit score in this physics paper. And 120 will be a very nice score in this paper because calculation mistake can happen. But this paper is very similar to what you're going to find in your exam. As far as my experience of 25 years for IT is concerned, I find this paper to be very similar. So just focus on this, try to make less mistakes and try to think more, write less so that you save some time also. So like that is the idea. Okay, students, bye-bye and take care. I'll see you in the lecture.